The Power of Simulation, a CHM152 project by Al-tekreeti. Me. Introducing my topic, the specific definition of simulation that I'm talking about is the imitation of the operation of a real-world process or system over time using computer models. For this project, I wanted to learn more about how computer simulation has helped the study of chemistry and advancing our understanding of it in various different topics that we have learned through the semester. And I wanted to prove that well-applied computer simulation can help students further understand many chemistry topics. First, I'm starting off with ensemble simulation. Although past knowledge can be used to determine the identities of key intermediates and rates of exchange among them, tremendous strides have been made in the discovery and use of methods to methodically assess states and rates using biomolecular simulation in the past few years. Ensemble simulation provides an efficient way to estimate biomolecular kinetics and rates. It can estimate structural transitions and kinetics of various viruses like coronavirus, and it can also, which helps a lot of students learn more about how kinetics works, on how kinetics work in the atomic level. And this is how it works. The arrows in A estimate where all the different pathways for the system are located, so it can make those four colorful models in B, in picture B. Those four kinetic models, those four colorful models are the kinetic models in the system, and the colorful arrows that are going between them are actually the transition rates between each model. And over here, so another power of the ensemble simulation, it can find different structural changes in viruses. So this is a picture of the coronavirus, except in one picture it has a version where the RBD is down, and another picture where the RBD is up and the virus is activated. Molecular dynamics simulation. This is another type of simulation that is used in many ways in the scientific community. It's used to determine the various properties of molten pure alkaline, aka basic, nitrate salts. Example, NiO3, NO3, NaNO3, and KNO3 when they are molten under high temperatures because those are normally neutral. And they determine the densities of them, the thermal conductivity, viscosities, and heat capacities. And molecular dynamic simulation can also identify those properties in mixtures of those nitrate salts, of those basic nitrate salts. And this is how it works. It defines initial values of the position and velocity of the particles, calculates the force of the particles, solves the Newton equation, and calculates the acceleration of the particles, predicts the new position and velocity of the particles, and then it calculates the kinetic energy and checks if the temperature agrees with the set value. If it doesn't, it adjusts the velocity of the particles. If it does, it checks if it's the last time step. If it isn't, it goes through the whole process again. If it is, it outputs results and it ends the simulation. That's exactly how it works. And over here is a comparison between the simulations numbers and the actual numbers that are written in books and literature. And it has approximately a 1 to 4% range of error, which is pretty good. So over here, I want to talk about Google's weak quantum computer. Google recently successfully simulated a basic chemical reaction, and the computer they used was just conventional. The quantum computer used was just as powerful as a conventional computer. So this is brain. So this new information can make it way more easier to perform reactions and in using school computers, so students will be able to learn more about how chemical reactions work at the molecular level with the help of artificial intelligence on just conventional school computers. And I want to speak about how important it is to have simulation with good analogies. So in this experiment, some scientists presented a computer simulation about Le Chatelier's principle. First group used a computer that has a analogical simulation. It had an analogical example in the simulation. And the second group used a computer that has the same simulation, except it didn't have an analogical example. The first group who had the analogical example scored a total of 90% on the test that they were given, and the people who didn't have it scored 68%. This This clearly shows how helpful simulations can be, and how helpful good simulation can be for students to use and learn from. And this is the picture. So on the left, you see the analogy window is enabled. On the right, you see the analogy window is disabled. And this is my sample calculation and balanced equation. It uses the numbers from this Le Chatelier simulation, and I basically solved the question: what happens to the concentration of PCl5 if the number of moles of Cl2 changes to 30.0 moles? So there you go. So the number in the end changes to 30.0 moles, and eventually I get an answer of negative 5.8 moles of PCl5. In real life, this number would be zero, and we wouldn't have been able to make that much Cl2 with the reactant we were given. But because this is a simulation of a reaction, negative numbers can occur. So we needed about 5.8 moles more PCl5 to get 30.0 moles of Cl2. This calculation shows that another advantage of simulation is demonstrating theoretical answers instead of logical, and that can help a lot of students understand something like Le Chatelier's principle better. And in conclusion, my research showed me how computer simulation was used in many different ways and topics throughout the scientific chemistry community, and that helped me learn a lot more about the concepts that we learned in Chem 152. Specifically, I showed that computer simulation can be used to demonstrate various concepts in a more theoretical manner, so students can get a wider or better understanding of the concepts they are studying. Finally, I also think that my data clearly shows the usefulness of simulation and how versatile its uses can be in a learning environment. Thank you so much for listening.